Hello everyone, welcome back to my YouTube channel. This is Neha SG, currently pursuing BE in Sri Venkateshwara College of Engineering from the Department of Basic Science, subject Mathematics, subject code BMATH 201, and today's topic is Conservation of Laws, Electrostatics in Mathematics. Introduction to Conservation of Laws, Electrostatic. Conservation laws in physics states that the certain physical quantities remains constant over time, such as energy or momentum. In mathematics, conservation of laws refers to a principle that describe the preservation of certain mathematical properties in a system. Electrostatics is the study of stationary electric charges and their interaction. Gauss law in electrostatics. Gauss law in electrostatics states that the electric flux through a closed surface is proportional to the total charge enclosed by the surface. Mathematically, Gauss law is expressed as the divergence of the electric field vector equals charge density divided by the permittivity of the medium. This law is the fundamental principle in understanding the behavior of the electric fields in different configurations. The formula for Gauss law is phi is equal to phi of E into ds. Conservation of charge. Conservation of charge is a fundamental principle in electromagnetism that states the total electric charge in an isolated system remains constant over time. Mathematically, this principle is expressed as the continuity equation which describes the conservation of charge in a given volume of space. Conservation of charge is essential in understanding the behavior of the electric currents and the flow of charge in circuits. Faraday's law of electrostatic induction. Faraday's law of electrostatic induction states that a change in magnetic field through a closed loop induces an electromotive force in the loop. Mathematically, Faraday's law is expressed as a line integral of the electric field around a closed loop equals the rate of change of magnetic flux through the loop. This law is crucial in understanding electromagnetic induction and the generation of the electric currents in conductors. Conservation of energy in electrostatics. Conservation of energy in electrostatics states that the total energy in an electrostatic system remains constant over time. Mathematically, the energy stored in an electrostatic system is given by the integration of the energy density over the volume of the system. Understanding the conservation of energy is essential in analyzing the behavior of the capacitors, electric fields and electric potential energy. Ampere's circuital law. Ampere's circuital law relates the magnetic field around a closed loop to the electric current passing through the loop. Mathematically, Ampere's law is expressed as a line integral of the magnetic field around the closed loop equals that the total current passing through the loop. This law is essential in understanding the magnetic field produced by electric currents and in analyzing magnetic fields. Ampere's circuital law states that the line integral B, that is dl, for a closed curve is equal to mu naught times the net current I threading through the area bounded by the curve. Conservation of momentum in electrodynamics. Conservation of momentum in electrodynamics states that the total momentum in an electromagnetic system remains constant, taking into account the momentum of both the fields and the charges. Mathematically, the conservation of the momentum is expressed as the time derivative of the momentum density equals the divergence of the Maxwell stress tensor. Understanding the conservation of momentum is crucial in analyzing the interactions between the electromagnetic fields and charged particles. Maxwell equation and conservation laws. Maxwell equations are a set of four fundamental equations that describe the behavior of the electric and the magnetic fields in the presence of charges and current. These equations incorporate Gauss law for magnetism, Faraday's law, and Ampere's law with the Maxwell additions of the displacement current. By applying these equations, one can derive various conservation laws in electrodynamics such as conservation of charge, energy, and momentum. Application of conservation of laws in electrostatics. Electrostatic conservation laws in electrostatics have various practical applications such as in designing electrical circuits, understanding electromagnetic waves, and analyzing the behavior of the charged particles. These laws play a crucial role in technologies like electric motors, generators, antennas, and capacitors. By applying conservation law in electrostatics, engineers and physicians can predict and control the behavior of the electric and the magnetic fields in different systems. Conclusion: conservation of laws in electrostatics is a fundamental concept in mathematics and physics that describes the preservation of certain qualities in a system over time. Understanding these conservation laws, such as conservation of charge, energy, and momentum, is essential in analyzing the behavior of the electric and the magnetic field. By applying these principles, researchers and engineers can develop innovative technologies and solutions in various fields, ranging from electronics to telecommunication.